All right, good afternoon, everyone. How's everyone doing today? Well, thanks for coming out to our talk. We have Blake Taylor, Magic Leap's head of graphics. We have Tonandi's lead engineer, John Cannon, and myself, co-director on Tonandi. So in case you haven't played the demo, here's a trailer to give you an idea of what that's like. Whoa. Those are some subwoofers, huh? So the story of Tonandi goes back a couple of years when our CEO, Roni Abowitz, invited Sigur Rós to our headquarters. And at the time, we still just had what was called the Beast, and it was this massive prototype. It didn't move. You basically stick your eyes into it, and you saw a 3D image. And from that, they were able to really extrapolate, where would it be when we finally launch? And so they got into a room and basically blue skied some concepts, and what they arrived at was this idea of music spirits, which is the actual translation of the title, tone spirit in Icelandic. And so the idea was that these music spirits would inhabit your space and together form like a musical soundscape, and it'd be totally interactive. It would be nothing like listening to a typical album at home. So when I got involved with the project, these are some of our early prototypes. And again, this was long before we have what we have today, the Magic Leap 1. These were all developed on pretty high-end PCs, and at the time, we didn't even really know the specs that we were shooting for with the project. So, because this was developed on a high-end PC, we didn't pay too much attention to the profiling. The example in the middle is literally dozens of rigid bodies in different colliders in order to get that sort of soft body feel. And on the right example, we're totally mangling Unity's built-in particle system. We're like pushing tens of thousands of particles around every single frame via a C# script. And so we were up for a rude awakening when we finally got on the Magic Leap 1. And so when we finally saw the performance, there were some scenes that were just terrible. Like, here's a pretty extreme example, but it was clear that the frame rate was not keeping up with the system. And in order to have a really good experience with Magic Leap 1, it really needs to keep up with 60 hertz. So with that, I'm going to hand it over to Blake Taylor to talk a little bit about doing that.
All right, thanks, Mike. So as Mike mentioned, the minimum platform performance requirement for us is 60 hertz. And this is a little different than 60 frames per second. Like intermixed in some of the talks you may have heard today, some people mention 60 FPS, some people mention 60 hertz, but really we want to kind of separate out what that definition means. And this means that at 60 frames per second, think about what that measures. That just tells you that in a 1 second period, you got 60 frames. You could have gotten them really fast, could have gotten really slow, they could have been scattered throughout that period. It doesn't tell you anything about the pacing or when those frames hit the platform to be used at the platform level. So in order to provide some place for developers to start for the platform, we came up with some guideline budgets to target on there. And these budgets, when you follow them, will almost always guarantee you a 60 hertz cadence on our platform, kind of regardless of the different system level variants or other issues that you may hit during runtime. We recommend that on the CPU that you target around 14 milliseconds. This leaves you a little bit of headroom frame to frame for any sort of variance that will keep you from falling out of pace on the CPU timeline. For the GPU, you're on a platform where the graphics surface is going to interrupt you, preempt you to execute composition at a completely different rate than what you're executing your app at. This is how we maintain pixel stick, handle our distortion, everything else that's needed to be done for the lightware. So we're going to come in and interrupt and chew up a small amount of the budget. In order to give you like good headroom, we ask that you target around 12 milliseconds. If you breach that or go much higher than that, you might still be okay in some scenarios, but in general, you may start hitting issues where you get thrown off cadence. Those two, the CPU and the GPU, are just kind of like high-level numbers, but the one that really matters is this total budget, CPU to GPU, because as a lot of you may know, the CPU and the GPU execute on completely different time domains. So the CPU is executing, and you don't know what, whether or not the work that you've already started on that frame has begun on the GPU yet or not. That's usually hidden from you at the driver level. What we ask that you target is to just look at your total budget. This is the time from when the frame starts on the CPU to when the frame ends on the GPU. And if you can really target around 22 milliseconds, that will keep you on a 60 hertz cadence. And if anyone wants to see that diagram after this session, I will happily sit down on a piece of paper and we can draw it out so you can understand. Because it might seem like a weird number, but it will keep you in line with that budget. So let's kind of dig into this a little bit further so you understand exactly kind of why it matters about hitting the 60 hertz cadence. So this first example right here, I took one, I said, I have an app that hits 60 frames a second, but it doesn't maintain a 60 hertz cadence. I have 3 frames here with their CPU and GPU times for CPU 1, GPU 1, 2, and 3. And you can see that for the first frame, it stays on cadence. It's well within that 22 millisecond period. But in the next frame, oh no, like the GPU spikes all of a sudden. Something new pops into the scene, something unforeseen happens in the game, just some random case that hopefully is random, not consistent at runtime, but some random case pops in that throws you off your cadence. So what ends up happening? What ends up happening is instead of us settling into a nice pattern where we're going to rewarp your frame on cadence on the platform, we get an extra rewarp. And it might be more than one. In this example that I show right here, it's just a minor bump. If you have a huge stall of 10, 15, or more milliseconds on the GPU, all of a sudden the platform has to try to make up the fact that you haven't provided a new frame to it. And there are limits of time warp. It's only going to save you from so much at the end of the day. The next example on there is for the third frame, the CPU spikes. So for example, this might be a case where a new shader comes in at runtime, or maybe you have a state-based recompilation, some other problem or unforeseen case on the CPU, again, pushes you off your timeline. And now we're really in a bad scenario because we spiked on the previous frame, and again, spiked again here, and now the composition is trying to make up for you this at the platform level. So what do we want? We want a stable cadence. This is what we want to see on your app, this timeline that I'm showing right here. The reason why this works is that if you look at every one of these frames, the total time from the CPU start to the GPU end is less than 22 milliseconds. There is variance. You can see that sometimes the CPU is faster or slower for some frames. Sometimes the GPU is also faster or slower. And where they're executing relative to one another is different and varying slightly. But taking all that variance into account, the total time is always 22 milliseconds. And this settles into a really nice pattern that I wanted to highlight here for the platform. So we have 2 features at the platform level. One of them is phase alignment, and one of them is horizon prediction. And if you're able to maintain your cadence at the CPU level, we're able to give you a horizon prediction, which means that we know exactly when your frame is going to show up on the wearable, and we have to predict and give you a predicted head pose for that time in the future. But if you're on cadence, we can give you a very, very accurate predicted head pose. What this means is that for the first frame, the composition picks up your newly completed frame on the platform, which I've highlighted with the green arrow. That frame that you generated, whether it was 30 or 40 or 50 milliseconds ago, is still really well aligned to the lightware so that the reprojection that we do at this time is very minimal, a minor patch up. This means that the bulk of the reprojection happens in the next composition period. And what this allows you to do is we have a lot of knobs on the API that you can program in better ways. Like you can provide us better inputs for constraining your near far or giving us different stabilization depths to help support warp. But the most important thing is, independent of all those knobs that you can send to us, if you can maintain this cadence at a platform level, we can pretty much save you from yourself, even if you're not programming the API optimally. So Mike, knowing the platform requirements of the system, how did that shape the vision for Tonandi?
Thanks, Blake. So now what, right? It was pretty clear what the problem was. As Blake outlined, we were just taxing the CPU way too much, and we had just learned that Magic Leap 1 was going to be shipping with this amazing graphics card from NVIDIA, and we were like, okay, why don't we try and make use of that somehow? In addition to that, all these new features were starting to come online at Magic Leap. So the hand tracking system. How amazing would it be if you could reach out and literally touch some of this virtual content? Again, the world meshing system. This, if you've tried Magic Leap 1, you've been able to mesh out the room. That was starting to work, and we really wanted to create an experience that really transforms depending on where you're playing it. So if you're in a small environment like a bedroom or a larger environment like a living room, we wanted these things to adapt the experience. Spatial audio. Because this is a music experience, this was an opportunity to really reinvent what the album listening experience could be like. So what if you took the different music stems in a piece of music and really separated it out in the space? And again, all these things are just more taxing on the CPU. So how are we going to move that over to the GPU? And around this time in the company, John Cannon joined our team, and he had some experience with what's called compute shaders. And so we started looking into how to really leverage those. So here are some elements from the final shipping version of Tonandi, and many of the elements on the screen right now are hardly being used on the CPU at all. A lot of this stuff is being simulated entirely on the GPU. And things that would have been impossible on the CPU, like the school of fish of 4,000 independent fish swimming around, that would have been impossible, and suddenly it was within reach on the GPU. So that way of thinking really crept into the design of all our elements. And so we're going to start to break down some of these over the course of the speaking session or whatever. And we'll just start with some of the more basic particles and move into some more of the complex and sophisticated stuff like the fish and the grass. So with that, I'll hand it over to John to talk about how some of the compute simulations work.
Thanks, Mike. So all of the compute simulations in Tonandi follow the same general pattern. So we first set up our simulation data in a GPU buffer. And this is information like the initial position and velocity, et cetera, of your particles or whatever you're simulating. And then every frame, we use a compute shader to update the simulation data and step that simulation forward in time. And then we draw the data to the screen for the user. And in both of these last two cases, the compute dispatch and the draw call, we're using indirect methods. And the difference between an indirect method and a regular draw call is the amount of CPU overhead involved. So with an indirect method, you package up the parameters for the draw call or dispatch into a GPU buffer, and you pass that to the function to do the draw call. And with an ordinary draw call, those same parameters would be passed as arguments to that function and then validated by the driver and then put into GPU memory for that actual execution. So with the indirect method, you bypass all of the validation and it's already in GPU memory. And this works really well if you're using a static size for the draw or the dispatch as well, or if you're generating it from a compute shader. So to give you an idea of how the shader side of this will look, I'm going to walk through part of an example that we're going to release after the conference. And so in that example, you'll be able to see how we set up all of the indirect buffers and the draw calls and all of that, but we're not going to go into all of those details in this talk. But looking at this, so this is a compute shader for Unity that works for a very, very simple particle system. So we have an array for the position and an array for the velocity. And in HLSL terms, those are read-write structured buffers. And so what's going to happen is every frame we're going to dispatch this shader, and this simulate function will be called for every single particle in the system. And it's going to update its current position based on the velocity multiplied by time scaling factor. So it's a really simple particle system that's not going to be too interesting, but it gives you the idea of how this works. And now to render that data, this is an example of a part of a material shader. So this is the vertex shader that's going to take the position from that same buffer that we just updated and use it in an instance draw call to position a mesh instance at that position and render it. So what we do is we look up the position based on the instance ID, and that just gives us the index of that particular particle in our position buffer. And then we transform that into view space. And then we add the vertex position for our mesh instance. And the reason that we're doing that in view space is so it will be billboarded towards the user. And then we multiply by the projection matrix to get into clip space, and the rest of it's fairly straightforward, normal shader. So let's talk about particles in Tonandi. When we first started exploring compute shaders, an obvious thing in the project to try to move to the GPU were the particle systems. Because each individual particle they operate independently, so there's no dependence on the values of the other particles. And the first thing that we made actually is this vortex that you see on the slide. And because this was a lot faster than what we had on the CPU, we were orders of magnitude higher number of particles. We were able to get into like 100,000 particles pretty easily. We wanted to start experimenting with different behaviors. So we moved to making just a generic GPU particle system. And the idea there was that we would have an update shader that we could replace. So each individual system, the only difference would be the update shader that did the actual simulation. The rest of the scripts that managed the draw calls and all of that would stay the same. And also at the same time, we set a kind of milestone for ourselves to try to hit 1 million particles per frame. And in doing that, we added a couple of optional features to the system for frustum culling and level of detail for the mesh. And the way that the frustum culling works is we check during our update shader if the particle is within the frustum of the camera. And if it is, we write it into a second buffer, and then we just draw from that buffer. And at the same time, we wanted to try rendering different meshes for each of the particles. And what we had started out with was a geometry shader that was expanding those points into just a quad. But we switched to doing the instanced mesh so that we could change the appearance of the particle system. And we'll go a little bit more into detail about that. But at this point, with all the high-level architecture in place for our particle system, we needed to start looking at the more lower-level performance characteristics of this. And so Blake, what can you tell us about how data layout affects this?
Thanks, John. So there are two options for your layouts when you come to attributes, especially in the pipeline that we care about. One of them is called array of structures and structure of arrays. And if you've been in the graphics industry, these are well-known terms. They each have their benefits. You know, to define them, array of structures, it has all of your attributes just packed together sequentially in memory. So in my example here, I've got a position, a normal, a texture coordinate, and they all get packed next to each other all in one block of memory. The structure of arrays is the opposite definition. And what ends up happening here is each one of these attributes gets their own block of memory. All the positions go in one, the texture coordinates in another, and finally the normals in yet another block. So let's talk about the benefits of each. The array of structures is great as long as when you go to access that memory, you're accessing all of those attributes at the same time. Otherwise, what's happening is you're pulling in memory, unused memory, for attributes that you're not going to reference that time around. Structure of arrays has a really nice property in that whether you access one or two or all of the attributes, for the attributes that you access them in the most cache-friendly manner. So in general, this is the most optimal layout, and for a generic system, one of the better layouts to pick on there. To highlight the benefits of it, to really take it home, I'm going to take that same example John just mentioned with doing vertex shading and positions. Using our two layouts, we have a diagram here where I show the AOS on the top. And for AOS, you can see that there's a 32-byte stride between the positions in that block of memory. And that's because the normal and the texture coordinate are sitting there, packed in memory, even though they're not being used. So let's say that you're on a system that's got a 64-byte cache line. That means you're only going to be able to shade 2 vertices or pull in 2 positions per cache line. It's not very efficient. You've wasted over half of that memory just pulling in attributes that you're not actually going to reference. However, in the SOA, you can see it's much more efficient. For each vertex that we're going to shade, we're going to pull in the corresponding position. And the positions are 12 bytes, float 3, 12 bytes apart. So you're going to get 5 of them per cache line at 60 bytes. This is over double the density that you see with the AOS. But additionally, you can improve upon this further. In systems where you have a penalty for splitting the cache line, meaning that you're reading across the cache line for one of those attributes, because it doesn't pad out nicely to the cache line size, you can pad each one of these to 16 bytes, and you're still going to get 4 positions per cache line with no wasted memory pulled in and double the number of positions that you had in AOS. So John, knowing the benefits and trade-offs of these, which one did you end up picking for Tonandi?
Surprise, we picked the SOA layout. For a couple of reasons. So as Blake mentioned, it gives us better cache performance. So if you think back to that compute shader I showed earlier, we had both a position and a velocity. And those were used in the compute shader to do the update. But the rendering shader only needed the position to draw them. So we got that benefit there. And also, so this snippet that's on the slide is actually from our actual particle system. Although I did notice when I was looking at this earlier, these should be read-write structured buffers, but just ignore that. So additionally, we define all of these as float 4s so that multiples of them will end up being fitting in a single cache line. And the second reason that we wanted this layout is the flexibility it gave us with our generic system. So we defined one position array, and then we have up to 8 custom attribute arrays. And then each particle system can use as many or as few of these custom attributes as it wants, and the only thing that has to know the meaning of those values is the compute shader itself. So the rest of the system, the rendering and the script side, they just have to know how many there are, and that's all there is to that. So then we started looking at other performance characteristics of our particles. And I mentioned that we switched to instanced mesh rendering. And when we did that, we also gained a mild performance boost. And the reason for that is that we were previously using a geometry shader. And if you know much about graphics pipelines, anytime that you use a geometry shader, it kind of introduces its own inefficiency into the pipeline. And in this particular case, we were using it just to generate geometry, and that's not really an ideal use case for a geometry shader, especially if it's generating the same geometry for every invocation. But then when we switched to this, we started experimenting with different types of meshes. Originally, so we were using textured quads, and if you have a very large quad particle on screen, all of those areas outside of the circle defined by your particle texture are just going to be wasted calculations of looking up the texture value and then outputting black. So we decided we wanted to try using a mesh that would cut off those areas. And so we tried hexagonal meshes and octagonal meshes. But when you start going this route of using a more intricate mesh, you run into another problem. And that's that you really want to balance your pixel coverage and your fragment and vertex shader workloads. So for example, if you have a relatively small number of large particles, large on screen, it might make sense in those cases to use the more intricate mesh and save that fragment shading on the outside. But on the other hand, if you have a really large number of really small particles, you're not going to gain much by eliminating those corners anyway, but you're increasing the vertex shader workload. So a solution to this might be to use an LOD system where you use simpler geometry for the really small particles and then the more intricate one for the closer particles. And so to look at that a little further, on our platform, what you really want to do is try to target at least a 2x2 pixel coverage for each triangle. And the reason for that is that when you start going below the 2x2 coverage, you're going to be shading more vertices than you are pixels. And that's going to really imbalance your pipeline. And you especially want to try to avoid doing single pixel or sub-pixel triangles because it's going to make even worse problems. Now you can see on the top right of the slide an example of the quad, the hexagon, and the octagon, and you can see how fast that coverage degrades as you go to the higher level or higher number of triangles. Now this same advice applies not only to just particle meshes. The other mesh that you see on this slide is actually the vein structure for one of the jellyfish Tonandi. And even when you're fairly close to this guy in the app, these triangles are still going to be really, really tiny. So as I said, you might want to try to LOD this, but in this particular case, when we LOD'd it, we ended up with a very linear and blocky structure that we didn't like. So in this case, we do live with it, but it's not a particle. We only have 3 in the scene at a time, so it's not too bad. So at this point, our particles are running pretty well. But Mike, can you tell us about some of the more specific uses of the particles?
Thanks, John. Yeah, so as John was saying, we had sort of dipped our toes in using compute shaders, and we're starting to get more comfortable with what that workflow looked like. So we moved on to some more specific applications like this school of fish. And it might not look like it, but it shares very much the same characteristics that John just walked us through. At the heart of each fish is actually just a particle, has a position and it has a velocity, and we just started to stack some behaviors on top of that. So if you all have tried Boyd behaviors before, that's how you can really achieve some flocking sort of animation. So we stacked that on there, and then in order to get some hand interaction, we added a repulsion force. So anytime the system detects a hand, as you reach out to that content, it's going to cause all the fish within that area to repel from that point. And so once you start to stack up these behaviors, you can get some really lifelike sort of animations. And so we were really happy with that, how that turned out. Here's another example from the project. This is our grass system. And again, this uses the same principles that we just talked about. Each blade of grass is actually made up of 12 particles connected together with a simple physics formula called a Verlet integration. And all that's doing is just maintaining a certain distance between each particle, and then we render it as a blade of grass in the end. And again, we can just copy and paste that same repulsion code that we use from the flocking fish onto this grass system. So as you reach out into that sea of grass, it'll disperse in a very natural way. And none of this is going towards the CPU. It's all being calculated and simulated within that compute shader. So this was a huge win. And that's sort of an icing on the top. If you hit the grass hard enough, the tips will sort of pop off and float up into the air, sort of like dandelions. So we were happy with that effect. Here's a more complex problem that we ran into. So what you're seeing on the screen is an element we called the LIGHTSEED. And it's actually a very old technique of rendering an audio waveform called a l.e.a.p pattern. And all it's doing is rendering that waveform in essentially a sine curve in front of you. And we took that a step further by introducing a hand interaction. So as you reach out to that audio waveform, it'll actually bend and distort towards your hand. And then we take that distortion and feed it back into the audio pipeline. So you're hearing a distorted version of the sound that you're touching. So it's a little bit mind-blowing. But it was very taxing on the CPU. There's literally tens of thousands of particles going on here to create that shape. And of course, when we got it on the mobile platform, it was extremely expensive, and we needed to look for some optimization. So we looked to John again to try and find some solutions there. Thanks, John.
You're welcome. So moving the LIGHTSEED to the GPU is actually pretty straightforward because it's in essence just a particle system. Similar to the ones that we've already talked about. The main difference, though, is that we had to get the audio data into a compute buffer and use that for the simulation. So the compute shader does a lot of math using the current audio data and the hand positions to calculate the position and color for each of the particles. And when we looked at this with the profiler, we noticed something that was kind of unexpected. We had a whole lot of invisible particles being rendered. And that's just a byproduct of how the math was working, that they were ending up black in a lot of states of the LIGHTSEED. And so we wanted to try to get rid of those to speed the LIGHTSEED rendering up. And what we ended up doing is in that same compute shader, we convert the current calculated color for the particle into a luminance value to determine how visible it would be to the user. And we threshold them at like a 0.5% luminance, and we discard anything below that. And in a lot of cases for the LIGHTSEED, that eliminated up to 80% of the particles that were being drawn. And additionally, because these are being rendered as additive particles, they're additively blended, they weren't going to affect any of the virtual content behind them. And on a light additive display, you're not going to see the black particles either. Now, I do want to say here that compute culling can be really fast. In most of the cases that we do culling, it adds maybe 1/10 of a millisecond to our compute shader passes, but it can save you a large amount of render time. And as I mentioned earlier, when we added the frustum culling in that pursuit of the 1 million particle mark, that was the only way we were able to achieve the 1 million particles. So now let's talk about rendering the world mesh. In a spatial computing application, rendering the world mesh is really important because it's what gives you the occlusion of content that goes behind a wall or a couch. And in Tonandi, we also use it for one stylized effect that we'll talk about in a minute. On our platform, the most efficient way to render this mesh for occlusion purposes is with a depth-only prepass. So what a depth-only prepass is at the beginning of the frame, you render that geometry into just the depth buffer. So you don't write it to the color buffer. And the reason that we want to do that is that on our platform, the frames that you get to start rendering into are already cleared to black, so there's no point in writing the black pixels anyway. And that saves you the memory bandwidth of writing the black to the buffer. And additionally, you want to do this at the beginning of the frame so that you have the most opportunity to reject any of the virtual content that would be behind the real world meshes. So for example, this is an example material shader for Unity that would do that for you. And so this is very similar to just the plain unlit color shader that comes with Unity, with two exceptions. The Q equals background and the color mask 0. So Q equals background tells Unity to put this as early in the sorting order as it can. This is typically the same area where skyboxes would be rendered, for instance. And then the color mask 0 just tells Unity to disable writing to the color buffer. Now, things get a lot trickier when you actually want to visibly render the world mesh. So Mike, can you tell us about the surface growth effect?
Thanks, John. So at the start of the Tonandi experience, we wanted some element to sort of symbolize all these virtual creatures coming into your own space. And we stumbled across these amazing mood board images of slime mold growths. And we were saying, oh, this would be like an amazing effect to try and do on your own room. Unfortunately, we don't have UVs for the world meshing. And so when we were looking at something like this, we wondered, like, how are we going to pull that off? So unfortunately, we never pulled it off. But we came up with this solution here. So as these little meteorites spring out of the LIGHTSEED and land in your room, it causes these ripples to come out. And those ripples move over the surface of your room, creating the effect you're seeing here. And in order to get it to look a little bit more organic, we couldn't use UVs, so we looked to something like calculating noise to do that. So as you see on the edge of that ripple, it has sort of like an organic feel, and that's because we're running per-lane noise over that. But again, we were in this situation where introducing this complex calculation like noise over every single pixel in the room was just going to be extremely taxing. So we needed to figure out some way to optimize that. So I'll pass it back to John, as usual.
So the way that the surface growth effect works is for each of those pixels, it's doing a triplanar noise. And it's sampling a texture to get the noise value. So with triplanar noise, that means you're doing 3 texture samples per pixel to do that. And they're also, because we're trying to use it as noise, they're not going to be coherent texture samples, so they're going to be pretty rough. So what we ended up doing for this, because we needed to, there's a lot of that area that's going to be black in the effect. So we needed to get rid of all those areas that we weren't going to even see anyway. And so what we did is in a geometry shader, we check if each of the triangles in the world mesh overlap with the region that we know it would be affected by. So it's just basically a minimum and maximum distance check away from each of the hit points. And if it doesn't fall within that region, we just discard it. So by doing this, we were able to cut the draw time for this effect in half, or almost half, from 10 milliseconds per frame down to 6 in our average case. Now, because we're also removing triangles from the world mesh, we still need to maintain that depth prepass. Otherwise, we have holes in our occlusion. So here's a visualization of how that works. All of the gray areas that you see here would have normally been shaded black by this heavy shader. But all of the effects or the areas that you see right now, those are the ones that are being shaded. So there's still a lot of black that you can see here that's ending up in the final output. But it's just a byproduct of the edges of the triangles touching the regions that it affects. So you can see there's a pretty massive saving, especially at the beginning of the effect. So another thing that was a risk to our performance in Tonandi, and we had to think about early on, was our post-processing. And the reason that we had to think about this early is we had, as Blake mentioned earlier, we have about a 12 millisecond GPU budget. And anything that we're doing with these post-process effects are going to happen for every frame of the application. So it's going to reduce our 12 milliseconds to some number below that. And the two effects we're using for Tonandi are bloom to give that otherworldly glow to the content, which we're using just the mobile optimized bloom from Unity. And the other is a vignette to kind of soften the edges of the FOV. Now, the reason that these are kind of expensive is that they're reading and writing every pixel of the display. And that creates a lot of memory bandwidth traffic. And anytime that you start stacking these, that just makes the problem even worse. So what we wanted to do is try to reduce the complexity of this. And so we looked at the implementation of the bloom. And the basics of how it works are that it copies the final rendered frame to a lower resolution buffer or image, and then it thresholds that based on the brightness of the pixels so that only the really bright objects that should glow are left in the image. And then it blurs that to produce the glow layer that will then add back on top of that original image. And it's this last step where it adds it back onto the original image that we found an opportunity. So what we did is in that last step, we just combined our vignette into the same bloom shader. So we added one texture read to sample the mask for the vignette, which we're using a really small vignette texture. So it's 128 pixels wide. So that texture sample itself is going to be pretty efficient. And then we just have one multiply to multiply it into the glow layer or into the final image to do the masking. And what this did for us was that it allowed us to completely remove that second pass, and there was a very negligible increase in time on the bloom composite itself. So at this point, though, the application's running pretty well most of the time, except for our load time is somewhere around 1 minute, and we have some random hitches throughout the application. And when we looked at both of those cases with a CPU profiler, they corresponded with shader compilation. So Blake, what can you tell us about that?
Thanks, John. So as John mentioned, there was an extremely long load time going into Tonandi. And as you can imagine, for the type of work that they're doing and the fidelity of this workload, they had a lot of shaders. And these shaders were complex enough that on our platform, it could take several milliseconds per shader to compile. And together, as he mentioned, this could take a full minute for all of the shader compilation to complete, which means that from the time the user started the app to even being able to possibly see something on screen, there's still 1 minute of work going on. And additionally, there was this runtime hitching. And if you go remember back when I talked about cadence at the beginning of the presentation, if there is a CPU spike on there due to a shader compilation, like a state-based shader recompilation that's occurring at runtime because the driver decided to recompile the shader based on the current state, that will create a hitch on there. And you don't want that, because once you break that cadence, you're pulled out of the experience. You want the user to feel like this content is part of the environment that you're in. And anytime there's a performance issue or glitch, that immediately reminds them that this content is not real and it's not in the environment. So what do we have? So on the platform, we have what's called a system blob cache that we enabled. And so this is actually available for all GL or GLES applications. And it's programmable via the graphics API, as well as exposed as knobs or through the interfaces of the editors for both Unity and Unreal. You can enable or disable this cache, as well as set the maximum cache size and the per cache size entry size on there. Together, you can tune this to ensure that all of your large shaders or the bulk of your shaders will be in this cache at runtime. And what this means is that once you go through your application load at least once, the precompiled blobs can then be fetched on any subsequent load, which will completely eliminate this cost of compilation at runtime. For Vulkan, it's a little bit different. So for Vulkan, they have the notion of a pipeline cache object, and you can enable the pipeline cache, or you can siphon off those binaries and build them into your app. But because it is built into the API, we expect that the applications will create and manage this themselves as part of the feature of the language. So knowing that we have this blob cache available, John, how did you guys end up getting rid of the stalls in Tonandi?
So you're not going to believe this, but we turned on the blob cache. So we turned on the blob cache in Unity settings, and then we ran our application, and we didn't notice any difference. But this is expected, because we know how the blob cache works. So the first run of the application, it's going to build the cache as it hits each shader to compile. So then we ran the app again after we'd been through the experience once. And we noticed some significant improvements. The load time was down to less than 10 seconds, and all of those hitches that we were seeing have gone away. Now, it's important to mention that your results with this may vary. You might not have a 1 minute load time. In our case, particularly, we are very shader heavy, and the compute shaders in particular take a long time to compile on our platform. I also blame Unity for that because of the way it compiles the shaders. But yeah, there's no downside to turning this on, though. It's literally just a checkbox, and the default values will most likely just work for you, and it'll only prevent any unexpected issues that you might have run into with this. But we still needed to do something about the first run of the application because we didn't want a user to download it from the App Store and then just be like, this sucks, and just delete it. So what we did is when we had a release candidate of the application, we would run it on an actual device from start to end, making sure we saw every piece of content to generate that blob cache. And then we would copy that off of that device and include it in the MPK. So then on application launch, we just check to see if the cache exists. And if it doesn't, we copy our pre-generated one into its place and set it up to use that. Now to do this, we had to disable the automatic blob cache support in Unity and manage it more manually ourselves by calling the C API functions. So there's a little bit of work involved with that. And the reason for that is that Unity sets this up really early before you have any script access to change these things. Now, there's one caveat to the way that we're doing this, and that's that the GPU driver is the thing that actually manages what goes into the cache and what gets invalidated. And additionally, the cache file is tagged with the version number of the GPU driver. So anytime that the driver decides to invalidate the things or store things in a different way, or a new version number comes, it's going to invalidate your whole cache and you're going to go back to that bad experience. So this is something we're still trying to figure out how to deal with for Tonandi, and for my part, I'm hoping that we can just switch to Vulkan at some point and not have to worry about it. But it's something to remember if you go down this route. And at this point, the application's running really well and we're ready to ship it. So Mike, you want to review and wrap up?
Thanks, John. So we shipped it. So I hope those techniques are something that you might be able to apply to your own experiences. And just to recap some of what we talked about today, first, think about what optimization is actually useful. If you're able to cull some of the content or not simulate it because it's not in view, do that. That'll get you more savings than trying to optimize a fragment shader. Next, balance the workload between those shader stages. As John pointed out with optimizing that growth effect, we were able to cull many of the triangles that were doing the heavy fragment calculations. Next, try to use dispatch with indirect if possible. We use this on a lot of our particle systems and it saved us a couple milliseconds. Next, try to profile early and often. This is a given, but we fell for it, so try to get it on device, see how much you're using, and always keep in mind how much of a budget you have left, because that 60 hertz is really important. And I think the biggest takeaway for us building Tonandi is that art and tech can work together. This journey of ours started with essentially an optimization. We were trying to get something to work on a CPU, and we discovered compute shaders, and it completely changed our design process. We were able to do things that we had never anticipated doing, like that school of fish effect or the grass system. These were all as a result of learning compute shaders. So if you haven't tried them, I encourage you to go out and experiment and see how it can work with your own experience. And we hope to release some example code later. We're going to do a particle system with hand repulsion and all that. So we'll be releasing it on the creator portal later. Thanks for coming out today. And if we have a couple minutes, we could do some Q&A. Anyone got questions? Is that not working, John? Actually, as a show of hands, has anyone tried compute shaders before? Nice. Okay, good. You using it with Magic Leap? Yeah?
Hey. Great talk, thanks. Question, what optimizations are available for stereo rendering?
So I hope Mike's on. So for Unity, I think it's on. So for Unity, what you have available to you right now in a previous build was the single pass stereo instance option on there at the engine level. Really, this is something that, like John mentioned, in this case, your mileage may vary on it because this isn't a native feature of the engine, and a lot of the shaders do not work in this mode. So as far as stereo optimizations go, a lot of those are going to have to be rolled by you by hand in your integration. And in general, what we would like to try to see happen for a lot of cases is especially with scenarios like the depth pre-pass, as well as a lot of your post-processing passes, where you're going to, or non-post-processing passes, where you're going to have good temporal locality of access, we want you to emphasize spending your time implementing those in a stereo fashion. And in scenarios where your source data is going to be completely separate, you can pick or choose whether or not you want to implement those stereo optimizations. In the end, what you're trying to do at that point is save on CPU time. So if you need more budget on the CPU domain, you can spend time doing that. But in general, the biggest bang that we're going to get on here is trying to optimize the locality of memory access. So I'd focus on that.
In the case of Tonandi, we tried doing the single pass stereo, but because we're using all of these instanced rendering methods already, the way that Unity's stereo works is it's doing instance draws. So what we had to do is multiply the number of particles by 2 and send them to the right eyes, and it overly complicated things, which I went through and did for a lot of the content, and then I profiled it and it didn't do anything for us. So I just ripped all that back out and we went back to the regular.
Any other questions?
All right, for the compute shaders, is there a special recipe for the thread count?
It's a little bit of a dark art to figure out what you want to use for that. Yeah.
We use 256 for like everything, right?
Most of our particles are running with 256 for the thread count. The thing that you want to do with that is try to figure out how many registers your shader is going to use so that you can determine the occupancy, and there's a lot of math that goes into that, and so yeah, it's kind of a trial and error thing. Is probably the easiest way to figure it out. But I would start with something smallish like 256. On our platform, on the NVIDIA, it's going to run 32 at a time per shader unit, but it can kind of pipeline those together. So yeah, I would try 256 as a good starting number and then go from there.
Alan, I think we had one up front.
Yeah, I kind of have like a noob question, but I'm going to throw it out there.
I'm a noob.
For someone getting into compute shaders, do you recommend any resources?
Are you familiar with Kabibo? Isaac Cohen? He's like a graphics artist. His Twitter handle is Kabibo, Cabbibo. He's a big inspiration and friend. So he has a ton of stuff on GitHub if you want to check out his examples.
Okay, amazing, thank you.
There's one up here.
What's next for you guys?
If you got a chance to see demos, we worked on the Royal Shakespeare Company project downstairs. We were doing a vol-cap. So we were able to capture somebody and like do 200,000 points per frame, thanks to John.
Yeah, it's more particles.
Yeah, more particles. And a Tonandi update is coming later this year too, so we're hoping to add some more content.
Maybe time for one more.
Yeah.
How did you implement real-time audio effects?
So we actually started the project by building native plugins to do that. So we had echo effects, like bit crushers, all sorts of things as DLLs within the project, but that just became almost unmanageable. So we ended up just doing a lot of that on the C# side because we had moved so much to the GPU. We used a spatial audio system and just had scripts where you can basically just stack them together to add in other effects.
We're using some of the built-in.
Yeah, there's a couple built-in still in there, but it's a pain. In the back?
You mentioned that you have like 1,200 sounds, but how many of sounds can you afford at once?
At once? We stressed it out pretty hard. There's probably at least 32 going at any given time. We use Google's Resonance Audio spatial kit because this was before the MSA was available, and they designed it to be mobile friendly, so it was actually pretty performant. Any other questions? I got one more minute. Don't be shy.
All right. Well, thanks, guys.
Okay, well, thank you for coming out today.
Okay.